All right, we're looking at average value of a function today, page 286 in the Finney text, if you're following along. And I want to start you off by just giving you a couple examples here on the board. So you can write these down if you want. You don't have to write these down. This is just a precursor to the lesson. But if I were to ask you, okay, so option one, what is the class average here if these are the following exam marks? We've got a really small class. We've got 5 tests only. And everybody gets an 80. Okay? What's the class average? 79? Incorrect. It is 80, yeah. Why? Because you do 80 plus 80 plus 80 plus 80 plus 80 divided by 5. And because, this is 5 times 80 divided by 5, the answer is just 80. Okay. Yeah, it's amazing. Isn't that amazing? All right. Test 2, same class, test 2. Oh, and that just disappeared. That's not good. Test 2, these are the marks. Okay? Now, this is 80 as well. It is. Why? Because we've gone 2 marks down from 80, 1 mark down from 80, but we've gone 1 mark up from 80 and 2 marks up from 80. So you can see that this is still has an average of 80, right? We add them all up, divide by 5, we still get 80. You guys good with that? Okay, what about test number 3? Okay, so I've gone down 20, but I've gone up 20 with this other mark. I've gone down 10, but I've gone up 10. So you add them all up, you divide, you still get 80 for an average. Okay? Now, the graphs might look like this, okay? Here's the percent over here, right? And we've got 80 all the way across. So it's the average of all these values here. Well, it's just 80. The second one might look something like this. Okay, it goes up a little bit. Average would still be 80. You take a look at all these marks, and the average is still 80. The third one, okay, dips down a little bit lower and goes a little bit higher, a little bit steeper slope maybe than this one, and average is still 80. Okay. So what if 100 students, and each of them got 50%, the average then would be what? You got 100 students. Each of them get 50%. The average is 50%. It's just like this one, okay? There's 50%, they all get 50. Now, think about this. What if there was 100 students in this class, and each student got a different percent, and they covered all of the percents from 0 to 100. From 0 to 100. No half percents or anything, all just whole number percents. And so we'd have a graph that looks something like this, right? We had a 0, and we've got marks, 100 of them, all the way up, just everyone is accounted for, all the way to 100. Okay? Now, what's the average of all of these marks? Each student gets each percent that's available, whole number of percents from 0 to 100. We have 100 plus 0. Let's do this one more time. We have 99 plus 1. We have 98 plus 2. And we have 50 groups of these, right? We have 50 groups of those. So we have 50 times 100, because that's the sum we get, divided by 100. So the average is 50. Okay. So the average is 50. So, yes, yeah, good job. 50. It's 50. Now notice what we did here. We have this slanted line here, right? All the way from 0 to 100. We did have this line where we had 100 up there, right? The average is going to be 100. Here the average is going to be 50. Okay. Now let's keep this in mind as we move on here. The average value, okay, of a function, would be the average value of the y values. So the average of all the y values of a function over an interval. So it's kind of similar to the example of we have 100 kids in the class, and every student gets each of the percents available from 0 to 100. I'm trying to get this all on one screen. Okay? And it would be like taking all 100 of those, finding the average of all of those. From 0 to 100, the average is 50. Now think of a line, think of a graph. Okay? We cannot possibly take all of the points between this point right here and this point right here. We cannot consider all of those points, because really technically there's an infinite number of points between the beginning and the end. Even on a finite partial domain, there's an infinite number of points. Because there's an infinite number of them because they're really infinitely small. So to stack them all together, you need an infinite number of them to make anything. So you can't count all the points, but if you split this up into 100 values evenly, you could kind of get a representation. You could also split these up to a little less than 100. You could split them up into something a little bit more reasonable, and that's what we did here for this example. So I want to find the average of all of the values that are represented, all of the y values that are represented. And this graph is very similar to the class, the 100-student class, where somebody gets 0, then somebody gets 1, then somebody gets 2, somebody gets 3, somebody gets 4, 5, 6, 7, all the way up to 100. So I'm going to represent the values of the function by just like 1, 2, 3, 4, 5 points. Okay, and I've got the coordinates listed on the right here. So 0, 0 is 1. I've got 0.25 and 0.5. I've got 0.5 and 1, 0.75, 1.5, and so on. 1, 2. Okay, so this is my graph. And if I consider all of the y values, so here's the y values right here. If I add up all of those and divide by 5, I would get an average value for this function. Okay, so that's 0 plus 0.5 plus 1 plus 1.5 plus 2 divided by 5. What do we get? You should get 1, I think, right? You have 2 plus 1 is 3, 1.5, that's 2, that's 5 plus 0 divided by 5 is 1. So you get 1. And just like in our student example, our class example, the average was the midpoint there. Okay, the average was the midpoint. We started at 0, we ended up at 2, and the midpoint of that here would be, between 0 and 2 would be 1. Okay, average value. All right, that's one thing. What happens if we don't have a straight line? Okay, so this is where it starts to get important. If we don't have a straight line and we want to consider all of the y values represented from 0 here to 1, let's say on the x-axis, all of the y values represented, all of the y values definitely would be represented here, like all of them would be represented in between. But if we consider sort of the x-axis there, if we consider that as almost like a time interval or whatever, you can see that the majority of the points, okay, in this time interval, okay, now here's half the time interval right here. This is half the time interval. Notice that the majority of the points that we could consider, the majority of these points are less than, 0.25, let's say. Okay, a lot of them are. And there seems to be, if we were to continue at the same rate, there would be points that we would consider, but there would be kind of fewer points represented in the upper region. And that's the way you kind of want to look at this. So don't look at it to say, oh, it's just the average between 0 and 2, and it's 1. Well, when we have a graph like this, what you kind of have to consider is, how are these points sort of spaced out as if this was kind of over time? So that's why I've considered, again, the points on the same, with the same x intervals there. So what are the point values at 0.25? Well, here it's 0.03, you see. And at 0.5, we've got 0.25. At 0.75, we only have 0.8 here. So in this way, the average of the values is going to be quite a bit different than the first example. And just give me a second here. Okay, so down here I have a little snapshot where I have the red graph and I have the blue graph. So notice that when we take a look at the intervals, we can't just count each point because there's an infinite number of points. So we can't do math with an infinity of points, right? So when we take the points at regular intervals, you can see that the values of the points in the red, overall, the average value, it would hang out more in the lower half, you see? More of the points are in the lower half. Here, the points are evenly spread out in the blue graph. They're evenly spread out. So with a straight line, like this, the average value is the midpoint between 0 and 2 here. But in this graph, the average value would be lower because there would be more of a congregation of points in the lower half. So how do you find the average value, or would you, of this function? How would you approximate that? You would take all of these y values, add them up, and divide by 5, just like we did before. So if I did that, all of these divided by 5, add them up, I get this value, 0.625, okay? So that's the average value of this function, all right? And that's kind of the toughest part of trying to teach this, is that yes, all of the points are represented in both graphs, but when we talk about an average value, we have to consider sort of the time intervals, like the x is almost like a time interval. So, for example, if you're walking from here to the high school office, and I tell you, there's two of you, and I tell both of you, okay, go to the office right now. One person walks at a pretty steady rate to the office, and the other person walks really slow in the room here because they're just still chatting with you're still chatting with your classmates. And then you get kind of out in the hall and you realize, oh, I got to get to the office. And then you start to speed up and you get to the office. Most of the points that they have occupied over that time period have been in the classroom, right? That would be more like this red graph. More of the points that have been recorded over the time interval would be closer to 0. So the average should be a little bit less. Not 1, it's 0.625. Okay? All right, I'm getting somewhere with this, so thank you for being patient. Okay, so let's just review. You can think back to the averages on the tests as well, okay? If everybody has 100% average, then the average is 100, okay? Think about this. When we plot this on a graph, you can also consider the x values and the y values. They can actually map out an area, right? So x times y is the area here, okay? So area equals x times y. Now, the y just so happens to be the average value of this function. Okay, so keep that in mind. Y equals average value. Okay. Now, if I did something like this and drew this line right here, okay, so x and y still can refer to an area here, but this graph has a different area underneath it. This would be x times 1/2 y, wouldn't it? Because it's a triangle. So here we have area equals x times 1/2 y, let's say. Okay, so what's the average value of the function here? Well, it's half of y. You see, half y, isn't that interesting? That's the average value of this function. Okay, so the y, or now we'll talk about the height, let's call it height. Height of the average value is really the y coordinate. And this is where I'd like to kind of show you how this relates. So if a equals x times the average value, what that does is give you an area of a rectangle, right? That's x by the average value. And what's cool about this is that the area underneath the big triangle and the area underneath the red rectangle are the exact same. Okay? Okay. So what happens then? I'm going to erase this now. You guys are writing this down. That's good. You can write this down. But what happens now if I have a graph that looks something like the red one did? All right? Something like that. And so if we kind of consider this, the area underneath the graph is x times the average value of the function, then that would mean that the average value, which is about here, I could draw a rectangle and look at this area and look at the area that would be underneath this red curve. And yes, those areas are the exact same. So we're kind of coming onto something here. Remember where we started? We started up here. This is y, and so the area of this rectangle would be the same as the area of the rectangle that has a height of the average value. It's equal to itself, right? That's really where we started. So average value, x interval, and area under a graph are related. Okay? Average value of a function, the x interval, and area under the graph are related. So that's where now we are just this close to coming up to the definition of what is the average value of a function. It's not simply the halfway point between the minimum and maximum. It isn't. It has to do with area under the curve. Now, what do you think of when you think of area underneath the curve in calculus?
Integral.
You think of integral, don't you? Yes, you sure do. Okay? So, are you ready for this? The function average, or the average value of the function, is the height of a rectangle that would have the same area as the area under the curve. And that would be, of course, for the same x interval. So I'm going to get you to jot that down. And I'm just going to summarize a couple things that we've shown, and I'm going to get to the actual definition of what function average is when we get to this third example here. So the function average, or the average value of the function, is the height of the rectangle that would have the same area as the area under the curve. And that's for the same x interval, of course. So these examples on the bottom here, the first two we've done, actually all three we've done. So let's think about this for a second. The area under the curve is this straight line up top. What's the height of the rectangle that would have the same area as the area under the curve? Well, it's just x times y. It's x times y, average value of the function right here, this y, maximum y. This one, the area under the curve, is 1/2 xy, right? Because it's a triangle. So we've got the average value of the function is half of the maximum y value, right? 1/2 y right here. There's y, and here's 1/2 y. And finally, the curve here. So let's think about this. The area, you said the area under the function, okay, is the integral, and I would totally agree. So this area is going to be the integral between a and b of the function f of x.
Wait, is that x times y or x minus y?
It's x times y. Yeah. dx, so you write this as an integral. That's the area under the curve. Y is going to be our average value, or our function average. And the value of x, so that would be this distance between a and b. So how could I write this value of x with reference in terms of a and b? What is this distance in terms of a and b? It is b minus a. It's the span, it's the x span there. Okay? So now what we're going to do is we're going to rearrange this a little bit, and we're going to come up with our actual formula. So we're going to have function average equals 1 over b minus a times the integral from a to b of f of x dx. So the average y value of the function is the area under the curve divided by the x span, divided by x. And we see that in all these examples. Okay? I have a clipping from the textbook here below, so it's written a little bit neater. And the textbook and different places you'll see will use some different notation for function average. So average f, they have it a little bit different. It's the same thing. You'll see me write it like this. Okay, so take a moment to jot that down. So think about this. We have a random function, and I'm asking you, what is the average value of this random function on the interval from 0 to 3? And this is we're gonna very quickly get into, we haven't had any examples where the graph actually is below the x-axis. So we're gonna think about this. What's the average value of f of x equals 4 minus x squared on 0 to 3? So here's the sketch. There we go, can you see that now? Here's the sketch on the right. Okay, so think about the area under the curve. This is technically the integral here, the area under the curve. It's positive, the blue, it's positive above here, and it's actually negative down here, right? So the the area under the curve is actually kind of small because this is a positive area and this is a negative area. So let's jot down our function average is 1 over b minus a times the integral from a to b of f of x dx. And again, we're looking for, and this diagram actually has the answer kind of on it here. This value right here is going to be the average value. And it's going to form a rectangle that has the same area as the overall area of this integral. So again, remember what I said, this is a large area, but this is a negative area down here. So when you add those two up, you actually have a little bit of a smaller area. So the function average is going to be 1 over 3 minus 0 times the integral from 0 to 3 of 4 minus x squared dx. So we're going to integrate this by manually. So that's 1/3. When we take the integral, remember that is associated with its antiderivative, right? So what's the antiderivative of 4 minus x squared? 4x minus 1/3 x cubed. Very good. And we're going to evaluate that from 0 to 3. So I'll leave the 1/3 out there, hanging out there for now. And we'll do 4 times 3 minus 1/3 times 3 cubed. Subtract, and then this is going to be 4 times 0 minus 1/3 times 0, so just minus 0. This is going to be 1/3 what? 12 minus 27 over 3, so 12 minus 9 is 3, so that equals 1. Now that's the function average, which means that at y equals 1, for this span 0 to 3, 1 is the height of the rectangle that would be the exact same area as the total area represented in this integral. That's the function average. And if I just erase some of this stuff here, and you look at all of the values, all these values go from 0 down to 4 minus, what is that, 4 minus 9, so negative 5 here. So they go all the way down there, but notice that the higher concentration of points actually would be up here, right? Because it kind of starts to drop rather frequently. So the average technically is going to be above 0. It's going to be closer to the top than it is the bottom. And there you go. It's right about there. So there is kind of a, when I think of it, I think of a time aspect of it too. Like you kind of like grab a point every second or whatever. And where the collection of those points, that's where you find the average. So you grab a point, 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 you grab a point. Most of them are above the x-axis. The average of them would be 1 here. Okay? All right. Yes, there are going to be questions. We'll do some, later we'll do some exam questions. We'll do some AP exam questions that talk about function average. And there's some application questions as well. You know, when you think about a trip, an acceleration, you know, when you're accelerating from here to the store, if you are driving your car from here to the store and you start at 0 and you accelerate and you get to the store and you slam on the brakes, you're at top speed, you slam on the brakes right at the store. Well, most of the time you spent was away from the store, was closer to your start because you were going pretty slow. Your distance was not changing very much at the beginning, and then your distance was changing quite a bit at the end. Right? So it would be kind of like this, right? All your points are congregated kind of more up here, and so this is less. So the average would be here. Just like you going to the store, you know, you're accelerating, going to the store, and then boom, you stop. Well, here you've got points here like this, right? And they start to spread out once you get going faster. So more of these points are more dense, closer to home or whatever. And so there you go. You look at those. And the average is not exactly between the max and the min. The average is more, you know, down here, closer to here. So again, that's the way to think about it. Okay. Okay. I am going to show you now. I'm going to show you now how to use the graphing calculator to do this, because on the AP exam, you're going to be having calculator active questions, and you're going to have to be able to do this with the calculator. So we're going to pause right now. I'm going to get some calculators out, and we're going to take a look at the screenshots I made here, and I'm going to help you figure out how to do this. Okay, let's take a look at how to do this on our graphing calculators. We have the TI-83s here. So y equals 0.5x squared. That's where we're gonna start. Where can I put this thing? Oh, everybody can see. Okay. Put it right there. So y equals 0.5x squared. So what we're gonna do is we're gonna go to y equals, and we're gonna put in our 0.5x squared. We're gonna put in that graph, okay, in there, y equals. And that's the first slide right here. Then we're gonna do second function calculate. And number 7, you'll see there's an integral there. Have we done this before?
Never.
No? Okay. So number 7, you guys are going to love this. Okay, number 7. And it's going to show the graph. Now you can do this, you don't have to do this by graphing it first, but just tends to be the easiest. You have to plug it anyway. So graph it. And it'll ask you for the lower limit. And so that is basically, you're trying to find this, right? The integral from, what, 3 to 4, right? Of 0.5x squared dx. Now this is an easy one, so you could do this on your own, I know, but this is what you're trying to find. So the lower limit there is going to be 3. You just type in 3, enter, and then upper limit is 4. 4, enter, and watch this. There's the value of the integral right there. 6. Now it's in decimal form. It's not an exact value form, but you pump in your lower and upper limits, and you get this integral 6.16 repeating. Okay, so find the average value of the function. Well, that's just part of it. Now what we need to do is we need to take that value, okay, right here. And remember, we have to subtract, we have to do 1 over that times 4 minus 3. So the function average is actually, right, it's actually 6.166 repeating, divided by 4 minus 3. So 6.16 repeating, okay, or 6.167, whatever. You should round it. Don't put the repeating sign on there. So that's your average value. Don't forget to do the 1 over b minus a as well, or over b minus a. Okay, pretty straightforward. All right, let's try the question we did earlier with the graphing technology. Okay, let's try that with the graphing technology. So I'm now going to go back to my y equals there, and I'm going to clear that. I'm going to put in 4 minus x squared. I'm going to do second function calculate to get to my calculate menu where I have all those great options. I'm going to type number 7. Okay. Okay, and my x, my lower limit is 0, so I'm going to put in 0, enter. And then I put in 3, enter, 3. Okay, so the derivative, the value of all of this area, top being positive, the bottom being negative, the value is 3. So my function average is going to be 1 over 3 minus 0, and then I found this out, the integral here, on the calculator, and that's going to be 3. So it's 1/3 times 3, and we got 1 before, didn't we? Okay, so you can now use your calculator for some of these problems because this is going to be just part of what you're going to need to solve, and you're going to be able to go quicker here with this. Yeah.
So you won't need to do it by hand.
You won't need to do it by hand all the time. At times you will, and on the AP exam there will be parts of the exam where you won't have a calculator and you will have to show you can do this by hand. But there will be some questions. This will be buried in a question, and you'll have to find the average value. And you just need to find the average value. You don't have to prove to them that you know how to do it manually. You just have to find it and move on. So, okay. So here's the screen clippings too for that same question there, if you want to see that. So again, the function average, function value average is 1 here, and that would be the height of the rectangle that would have the same equivalent length. So the height and the same length as the interval in this question. That's a way you can think about that. All right, so what have we done? We have talked about average value of a function. We've also talked about how to use our graphing calculator to determine definite integrals. I can go over that process just one more time real quick. You go to your y equals screen, type in your function, then go straight to the calculate menu, and you push in 7 there for integral. Type in your lower limit, 0, upper limit, 3, and then it will sketch for you the area, and it'll give you the value of the integral down there. And I do have another video on AP calculus graphing tips, something like that. So if you want to watch that video, I do this and some other things that will be helpful for your AP exam you'll need to know. So I do have another video, and maybe I'll take a class with you guys and actually go over that before the AP exam. Okay, here's your assignment from your textbook, and I'd be happy to do the first question for you here, or with you anyways, to make sure you're on the right track. But that's it for this lesson. Any questions? What average value?